All right, so we're almost done with our gravitational field talk. In fact, we got two more things to discuss here. And so this is where we're going to talk about, like, gravitational field and acceleration due to gravity on different planets. Okay, so how can we kind of determine that? We could technically use factors of change to determine some of this. We'll actually derive a formula to do like actual calculations. Okay, and so we've been talking about this g value, right? That g value is what we call acceleration due to gravity. A lot of times students will want to kind of say, oh, this is just gravity, right? No, this is not gravity. This is acceleration due to gravity, right? So it's the acceleration an object falls near the surface of a planet. Again, right? Near the surface of a planet. This has no application once you go outside a certain, certain area, okay? One thing to note, it's always going to pull the object down, right? Because that's where the gravitational field wants to go. And here on Earth, we have a value of 9.81 meters per second squared, but we've been also using 10, right, to make our calculations simple. Now, one thing to note is that G, right, is also a gravitational field. Okay, one thing that we do to distinguish between the two, and I did not do it here, is we put a little arrow over the top of that G to say this is a vector, okay? And so once the object is in the gravitational field, it's what causes the gravitational force of m times g to be exerted on the object in the field. In fact, force of gravity, right, or weight in words, it says when placed in the gravitational field of a value of g, right, again, a mass m will experience a gravitational force of m times g, where g, right, the gravitational field strength on Earth is 9.81 newtons per kilogram. Or if we use 10, it's 10 newtons per kilogram, right? And look at this, right? There's one way to tell the difference between the acceleration and the gravitational field strength is to look at the unit. If it's the acceleration, it has the unit of acceleration of meters per second squared, right? Up here, meters per second squared. If it's the gravitational field strength, it would have the units. Oh, that's bad. Sorry. That's dark on dark, right? So it would have the units of, and I just made it darker. Right? And so you'd see it has units of newtons per kilogram. So when you see newtons per kilogram, it's actually the gravitational field, okay? And so how do we really distinguish between this? And so we're talking about near the surface of the Earth. So here's the surface of the Earth. This field points directly down, okay? One thing to note that, right, it acts downward, okay? And all of these essentially are field lines, which is the arrows that I drew, and these are what we call field lines, right? They're evenly spaced because the gravitational acceleration, right, is constant near the surface of the Earth. Right? We did that way back in the first video when we looked at the difference between Miami and Denver, right? Now, as you move away from the surface of the Earth, right? So here's my Earth, here's my field, right? Still, you'll note that it is directly downward, okay? That's it's still acting down, but here's the difference is that they're not evenly spaced. Okay, because what happens is as you go away from the planet, the gravitational field gets smaller. Okay, so yeah, the gravitational field at this point would be equal at this point, but it's different than down here, okay? And so when we do calculations involving like solving for this lowercase g, right, this acceleration due to gravity, it's going to depend on two things. One is going to be the mass of the planet, right? And two is going to be the radius of the planet. So sometimes you may get a problem that says, okay, what's the g value on Jupiter? And so you have to be given the mass of Jupiter, the radius of Jupiter, okay? It may say, okay, you've got you see this example, you have a hypothetical planet, okay, that has this and this. You know, what's the g value, okay, or how does it compare to Earth's? And so how do we get this distinction? Well, the weight of an object would equal the gravitational, and I'll put a big G for gravitational force, right, the Newton's law one. But if I kind of, what are the formulas? Mass, right? Fg is mg. F big G is g m1 m2 over r squared. Okay? And so what you do is, yeah, there's two masses in the second formula here, but one of them is just simply the object, and mass 2 is the planet. Oh, sorry, I got a little too close to the scroll bar. Okay? And so now when this simplifies, the g on any planet is capital G, which remember is the universal gravitation constant, times the mass of the planet times the radius of the planet squared. Right? And so you can see here when we're talking about what are the two factors, mass of the planet, radius of the planet. Okay? So there, you know, you don't have to worry about what the object is. You just kind of just plug it in. Okay, you just plug in the mass of the planet. And so if you want to do a calculation for Earth, it'd be 5.97 times 10 to the 24th, which is the mass of Earth, divided by 6.30 times 10 to the 6th squared. And when you do that, you're going to get approximately 9.81. Okay. All right. So now let's look at, you know, something typical that often will show up as a multiple choice question. A hypothetical planet has twice the mass of Earth. What would its radius need to be for the acceleration due to gravity near the surface of the planet to be the same as Earth? Okay, and so we're going to do our factors of change, but we're going to do it for our simplified version of the formula. Right? We don't have to do the big. We don't have to do like g m1 m2 over r squared. We can just do our little g formula that we discovered up here to the right, the g equals gmp over rp squared. Okay, and so we want it to equal Earth's, so we're going to say 1 for little g. Big G doesn't change. The mass of the planet is 2 times greater. Okay, and then we're solving for the radius of the planet, right? So we're looking for what is r equal, right? And so that's going to be 1 equals 2 over rp squared. And I'm going to solve this for rp. It's going to be rp squared equals 2, right? And so the radius of the planet would have to be a square root of 2 times bigger than the Earth. So if you want to, like, if it gives you actual numerical values, it would be 1.414 RE, or if it does keep it as the square root, it'd be root 2 RE, right? So these would be your answers. So how much bigger would the planet have to be? It would have to be, you know, root 2 or 1.414 times bigger than the Earth. Okay, again, using the factors of change. Factors of change method is very effective when you're using this type formula, okay? All right, so we're almost out of the gravitational talk. We just have this difference between inertial mass and gravitational mass, and then we'll do circular motion.